So welcome back everyone. Today we have Nilay again for the second part of his talk on inflationary cosmological correlators using conformal symmetry in momentum space. Nilay, over to you.
Okay, thank you. So let me start the second part of the thing that I couldn't finish last time. So I hope the screen is visible, no?
Yes, it is visible.
Okay. So let's start with some summary of the part one that we did last time. So we understood that inflation explains approximate homogeneity and isotropy of our universe. Additionally, it also provides a scope to generate tiny fluctuations that we can measure in the CMB. So this space-time was approximately d zeta during inflation, and we are focusing on a late time slice of the d zeta, which in the conformal time coordinates is eta equals to 0. Eta runs from minus infinity to 0. And at this slice, the fluctuations that were generated gets encoded in the cosmic microwave background, and we can observe them today. So we have also understood that symmetry play a major role, and this is so any analysis based on symmetry is definitely robust and model independent. So we can predict some form of the cosmological correlators that's obeyed by this symmetry, and we don't need to rely on model independent. That happens to be the theme of this work, this kind of work. And we have also understood that the de Sitter symmetries near the eta equals to 0 slice or the late time slice happens to be the same as the symmetries of three-dimensional Euclidean CFT, and we have decided that using the homogeneity of the spatial slices, it would be better to analyze things in momentum space. So these correlation functions of cosmological perturbations, which were generated during inflations, are encoded in the eta equals to 0 slice, which happens to be this slice, and then the techniques of conformal field theories can be applied on this slice. That was the idea, and we have looked at the metric during the inflation, and it was not exactly d zeta. If it would were inflation exactly d zeta, not inflation, then this h would have been constant, and there would have been no scalar field, but just a constant potential. So the perturbations were classified in scalar modes and tensor modes. So tensor modes with respect to the three-dimensional space, spin 2 with respect to that SO3 rotation available there, and the zeta and gamma ij. The zeta is basically the trace of this gamma ij, which can be seen here, and the scalar modes corresponds to what we see as temperature anisotropy in CMB, whereas this metric perturbations or tensor perturbations, they correspond to primordial gravity waves. Now, the next question that we would like to address is how can we compute these correlation functions? So we have these fields which are operating during inflation, and they were interacting with themselves, and they have some late time values on this slice. So how would we compute the correlation functions between these late time values of these modes? So I'm just showing a 3-point function, but as we will see, like we can obtain results for any point correlation function in principle. But in terms of cosmology, the 2-point function is called the power spectrum, the 3-point function is called the bispectrum, 4-point function is the trispectrum, and so on. And these are the measures of non-Gaussian unities, which we have discussed last time. So the question is, how would we compute these correlation functions? So there are various correlation functions. How would we compute at this eta equals to 0 slice. So there are two methods available which are bulk or de Sitter 4 methods. So the one of them will we will see that one of them is called the something called the function of the universe. So we should introduce this as we go along, and from there we compute this correlation functions. And the other, who is something which is well suited for de Sitter physics, because this is time dependent physics. So I mean, in other sense, non-equilibrium method, which is the Swinger-Keldy's formulation. So this is actually very well known in the cosmological community itself, and it has been used. Basically, people use this method only to compute these correlation functions. But today, I would like to introduce this method, which can also reproduce this. So this is also called in-informalism, and we will see why is the name uh, that. Now, from the CFT side, as we have understood that we're focusing on this slice, so we will have different operators corresponding to the time values of these different bulk modes, and we would like to understand how can we use uh, symmetry, like in the conformal field theory, how can we obtain different correlation functions. So in position space, we all know that the 2-point function and 3-point function is completely fixed up to some constants, and but here we would be doing momentum space analysis. So the question would be how to understand these correlation functions in momentum space. So these are two different approaches. Primarily the bulk approach, where there are two methods, and there is this CFT approach, where we will see how to compute things. So let me introduce this wave function of the universe understanding. So this is basically a path integral over the bulk fields that are there, delta phi tilde and gamma tilde and zeta also, which happens to be operating during inflation. And this path integral, the boundary conditions are important. So uh, at at the initial point, which is this eta equals to minus infinity slice, we should put some boundary condition, and at late time slice, this bulk fields have some boundary values. So I'm denoting this delta phi, delta phi, delta phi, gamma ij. All of them are happens to be the boundary value of the fields on which I'm doing the path integral, and this is called the wave function, and this is basically a functional of the late time values of uh, these fields. Okay, and this is this e to the power is, where s is the action which we have seen before, but now we have to evaluate this action for the metric perturbations and the scalar perturbations. So basically, if I solve the background geometry, which is de Sitter, or slow roll de Sitter, and the background field for the scalar field, then I can obtain an effective action, which should be an action in terms of this delta phi, zeta, and gamma ij. So this is the technical definition, or in principle, this wave function is defined like this. And most important is that since we are interested in the late time slice, so this is like the wave function is the all the information about the boundary values of the fields and their subsequent evolution during the inflation are encoded in in this in this uh, in this function. So we would like to compute the correlation functions using this wave function, and this will be the main player in the game. And as I told you already, that we need to put some boundary conditions for doing this path integral in the initial slice. So there are some boundary conditions. The traditional one is the Punch-Davies boundary condition, and we will also see that there are other possible boundary conditions, which are called the alpha vacuum. Now, uh, this Barnes-Davies vacuum or alpha vacuum gets related to one more very interesting question that we may be interested in asking, which is what initial condition did our universe start with? So, what was the initial condition for the inflation, and how does that get encoded in the late time slice, so that by looking at the correlation functions of the CMB and isotropies, how can we decide what was the initial condition? So that's why, are there any observational signatures? And we would like to address these questions. But this wave function defined this way, I'm doing a path integral uh, in this region and obtaining the information of the state of our universe at this slice. So this is like doing the path integral to know the ground state of a system, as we have seen in the path integral problems. So please feel free to stop me if you have any questions or comments. So we are exploring with the searchlight of conformal field theory. Now, both the boundary conditions, this Bunch-Davies or this alpha vacua, are consistent with conformal symmetry. So both these boundary conditions are conformally invariant boundary conditions, and this Bunch-Davies initial condition is basically saying that the modes in the far past were almost behaving like they were in the Minkowski spacetime. The de Sitter curvature is not recognizable for them. Basically, the wavelength of these modes, this delta phi, zeta, or gamma ij, are much less than the Hubble radius, so that they cannot see that the spacetime is actually curved, but they feel that they are almost in the Minkowski spacetime. So this is implemented in the path integral by analytically continuing the eta, which is the conformal time contour. This is the I epsilon principle that we study in quantum field theory, and then around this contour, one needs to assume that the modes delta phi, zeta, or gamma ij, they vanish as the zeta goes to minus infinity during this with this small imaginary uh, I epsilon attached to it. And as we will see later, this alpha vacua are like these modes didn't start in the Minkowski for the one stages, but in some excited state. But the most important thing is that both of them are uh, consistent with conformal symmetry. So if we are working with this principle that we should look for whatever is allowed by the conformal invariance or the scaling symmetry and the special conformal transformation, the full conformal group, then we should allow for this vacuum also. So what do we mean by this conformal invariance, or how
But
does, yes,
so the idea of Bunch-Davies vacuum was when I go to far past, it should look like Minkowski vacuum. That is
yeah,
what I. Is that the idea?
yes, near here the modes are almost like propagating in space.
Okay. Okay.
So their wavelengths are much smaller than the Hubble radius, and this Hubble radius is actually related to the de Sitter radius. So that's what I mean, that uh, this move, or operationally one should implement it like this. Okay. So what do we mean by this conformal invariance? So the conformal invariance, as I have defined this wave function at being the functional of the late time values of the perturbations, delta phi, gamma, ij. I'm not explicitly writing, but this collectively means all delta phi, theta, or gamma, ij, which are the perturbations in the metric and the inflator. Now, in the path integral, if we look at the path integral, the action is conformally invariant, the measures are conformally invariant. The initial boundary condition, whether it's Bunch-Davies or alpha vacua, for now I will be talking with Bunch-Davies. This is also conformally invariant, but the late time values will transform. The late time values, which appears here in the argument of the functional wave function psi, they transform under the conformal transformations. So the demand that the wave function should be conformally invariant is implemented by demanding that this delta phi uh, and if we do a conformal transformation and look for the change in the boundary value of the scalar field, the wave function when evaluated for this changed boundary value is equal uh, to the uh, to the initial boundary value. Now, one more question that we should understand is so knowing this wave function, how do we obtain the correlation functions? So let's say I'm looking for a 3-point function delta pi delta pi delta phi, and how would I obtain it? So the prescription for that is as simple. So we should understand this wave function is kind of giving me a probabilistic interpretation of for this perturbations, and I should do this further integration, which is this mod square. So the psi is like the amplitude, and mod psi square is like the probability. So this, if I have to take, 3-point function of the delta pi's, so I would have 3 delta pi's here. So I should have 3 delta pi insertions here, and then this path integral will sorry. So this further integral will then evaluate the correlation functions for me. And this is true for any correlation functions. Like if I am interested in this correlation function, which is a mixed correlator, scalar tensor tensor, then I will have that insertion here. Now, again, another issue that we must be taking care of is related to this major factor in the path integral. Now, this if we so this we are basically doing diffeomorphisms invariant theories. So, I mean, if I am this is basically doing a sum over this delta phi and gamma ij configurations, but different gamma ij and delta phi are related to each other by gauge transformations, which are like coordinate transformations. So if I don't fix that gauge, so I'm doing overcounting over here. So so this path integral is ill-defined without this gauge fixing. So to address that, we would like to work in the ADM formalism, where the metric is written in this form with this n and ni being the shift and lapse function. Then we should fix this gauge by making this choice that n equals to 1 and ni equals to 0. This is called this is the synchronous gauge. It has a name, and in that gauge, the metric turns out to be this one, where you can see this zeta and gamma ij appears inside this hij, and the scalar vector also has this perturbation delta pi, the fluctuations of the inflaton. Now, as it is true for any gauge, fixing, if I am fixing this n and ni gauge, so the equations of motion of them should be imposed. They should be treated as constraints, which physically mean that this wave function after this gauge fixing should be invariant under residual coordinate transformations. So this n equals to 1 and ni equals to 0 doesn't completely fix the gauge. I still have some residual freedom, and this wave function should be invariant under them. And those residual freedoms are like this, where I have some time deparametrization, so I can change time by some function of the positions with some associated rescaling or redefinition of the momenta. So these two together uh, keeps this form of the metric invariant. That's the statement. So I fixed this gauge and I've obtained this form of the metric, but I can still do this time reparameterization that keeps me in that gauge. This can be checked, and we can use this to fix something again. So this residual freedom can be used to fix either delta phi equals to 0 uh, or uh, or zeta equal to 0. So there is something wrong, not correct. This one. So this is one choice which I can make. I can in the scalar sector I can use this reparameterization to get rid of the delta phi and keep the full scalar degrees of freedom in zeta, or I can put zeta equals to 0 and put everything is in delta phi. And both these choices, these two choices, are related by some coordinate transformation like this, and that can be used to obtain some relations between this delta phi and zeta, so that at some point one can work with this gauge where delta phi is not equal to 0, compute the correlation functions delta phi, delta phi, delta phi, and then one can use this relation to obtain the result zeta, 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 which is appropriate in this gauge. There is also some spatial reparameterizations available, which is just xi being changed by some other arbitrary functions of, uh, of position. So one can also use that to so you can see that there are three degrees of freedom here, worth 3 degrees worth freedom here, because I can go from 1 to 3. So I can use that to fix the graviton, or the metric tensor perturbations being traceless. So it transverse. Sorry. So it was traceless from beginning because I was I was keeping the uh, trace with the zeta, but I can also make it transverse. So this is also sometimes called the transverse traceless graviton, being used in doing the inflationary calculations. Now, to do some calculation, I have not been very consistent with units, but as we know, in front of this gravity action, there is always this 1 over 4 pi or 16 pi, I think 16 pi g Newton, which is dimensionally same as m Planck square. 1 over g Newton is like m Planck square, and uh, and I can also do some rescaling to make the variables over here dimensionless, and this 1 over h can be taken out to have this m Planck square over h square sitting outside. Now, this is observationally we have understood that this Hubble radius, or the Hubble scale, is much smaller than the Planck length. So it means that this Hubble radius is kind of related to the energy scale at which inflation occurred, which is roughly like 10 to the power 14 GeV. H is roughly like that, and Planck length in appropriate units, one can say it's like 10 to the power 18 GeV or so. So one can check that there is this 10 to the power 8. So basically, what I'm trying to say is that this number over here is very large. So one can use this. This is something like large n approximation. So I can use saddle point approximation, where this integration will be dominated by the on shell action. So where I can minimize this delta s, delta phi to 0, and I can figure out I can solve for the equations of delta phi that we can obtain from this action, and then substitute it back in the action, and that's what this on cell action computes. So with this fact, I can effectively approximate this wave function path integral by something like this saddle point approximation, and also we can we can then use this fact that the wave function that like the correlation functions or whatever we observe in Planck data or like, any observations tells us that this wave function is nearly Gaussian, and so I can write this wave function, which is a functional of the late time values of the perturbations, to be something like this on this, which I've written on the right hand side, where I can see that this delta phi square term appears. So this is the quadratic term in delta phi. This is the quadratic term in the gravity perturbations. So this should be the leading order terms, which if I would have kept just these two terms, then the wave function would be exactly Gaussian. But we don't see it to be Gaussian, but there are tiny fluctuations or departure from non-Gaussianity, and uh, those are represented by these numbers, where you can see uh, higher point higher point moments of these perturbations are present. So I can have a delta phi cube, I can have two delta phi and one gamma ij, I can have one delta phi and two gammas, and then I can have gamma gamma gamma. Then these dots will be similar terms with delta phi delta phi delta phi delta phi, and so on. And all of them will be denoting the non-Gaussianities. Okay. Any question so far?
Nila, can you repeat once again how you got from E for IS on shell to this expression with 2-point function and 3-point functions?
Okay, so this is something like Largen approximation, as I told you. If I am very careful with units, then there is this factor that comes overall outside of the integration that I have in the action, like d4x
Right,
root minus g. Then it's an observational fact that inflation occurred at a scale which is much less than the Planck length.
right,
So much less meaning the hierarchy is something of that. So with that, I can come to this where I will have an
right,
on cell action. But then I'm using a different input or an independent input that we know also from observations, that the perturbations that we observe in the sky. So let's say I observe it in one direction, then I observe it in the other direction as a functions of angle, which is different positions in the sky. And then if I look at the distribution, that distribution is nearly Gaussian.
Oh, okay, okay.
So that also tells us that in a statistical distribution, if it was exactly homogeneous, I would have only obtained a Gaussian distribution. But if there are tiny fluctuations, then those will be captured by higher order moments. So in principle, I can always write this e to the power I on cell as some exponential, the same exponential, but this s on cell. So in a sense, if it was exactly Gaussian, then it would have been a free theory.
Right.
There would have not been any interactions. So these higher point functions is like interactions in this on shell action. So
Okay.
I'm writing in a very schematic form,
No,
but that should be the
huh,
form of the wave function.
right,
Yeah, I had a question.
Yeah,
So
please.
here, like, but this saddle point approximation, how does it differentiate between Bunch Davis vacua and alpha vacua? Like, uh,
Okay,
it,
so I am
uh,
I'm yeah.
yeah, I'm not able to understand how to like this analysis differentiates that.
That is also not clear. Yeah, that's also not yet under clear. So that I will come later. For now, I'm
Okay.
having bunch Davis, but even if there are alpha vacua, I don't know. I mean, we don't yet know how to formulate this wave function. But in principle, this is defined in this way, and it's just changing the boundary conditions here. So in principle, it should be one should be able to do this, but in practice, no one has ever yet done it.
Okay. Yeah. Okay.
So now, if you assume or if you agree that this wave function has to be a Gaussian function, then this part is okay. This delta phi, gamma, gamma, delta phi. Now, what are these OOTT, OOO, OOT, OTT, TTT within angular brackets? What are they? As of now, they're just some functions. So in practice, this delta phi will be at x1, this delta phi will be at x2. So this O will be any function of x1 and x2. Like this one will be any function with pair of indices and x1 and x2. But as you can understand that we are writing it, this is indicative of the fact that this will have something to do with CFT, where this will be a 2-point function in a CFT, but that's where we are going. I mean, I should be able to convince that these functions, which we now call just coefficient functions, these are just some coefficient functions. Now, some notation, let's say, some notation, but they're going to be some correlation functions of operators in a 3-dimensional CFT. That's where I'm going. So this invariance of the wave function now puts constraint on these correlation functions. Now, how is that true? I've already explained that the conformal invariance tells me that the delta phi, the boundary value of the perturbation, even if it's changed, the wave function evaluated on them should be equal. That's the demand of conformal invariance. Now, delta phi prime can be written as delta phi plus the change in delta phi, which I'm writing as delta times delta phi. But this side we know. I mean, I should just look at let's say scaling transformations or spatial conformal transformations, and I will know how delta phi transforms under that. So this invariance of the wave function should tell me how this O and Tij should transform. That's how we will realize that this O should be, so the idea is that this delta phi will change. So that's this will be some delta of delta phi. But when evaluated, the psi should be invariant. So I can change this delta of delta phi by some biparts integration and demand that this O are changing in a different in a negative way. So how should this O be changed such that even if delta phi changes, the psi remains invariant? So that will tell me how this O and this Tij should transform. And there we will see that these are exactly transforming as dimension delta equal to 3 or some operators in CFT. And that's how we will obtain the word identities. So in this whole discussion, I just want to make sure that there is a subtlety that one should keep track of, which is that we are looking for word identities or symmetry constraints of correlation functions of fluctuations around pure de Sitter space or inflation. So there are two things going on side by side. Once we are deciding whether it's a pure de Sitter space for which we have a Hubble parameter is a constant and there are no inflaton, there is just a constant potential, no kinetic energy or no evolution of the scalar field, and then they will match to exact conformal field theory word identities. But inflation is not pure de Sitter space. Inflation is some small corrections to de Sitter, and these are called slow roll. And on top of this background, there are fluctuations, and we are effectively looking at these fluctuations. So if we are looking at these fluctuations in the pure de Sitter space, or exact, I should say exact de Sitter space, then this is just doing quantum field theory in de Sitter background. But if I am doing these fluctuations in the inflationary slow roll inflation background, then I'm really doing, cosmology or inflationary correlation functions. Now, let me give you some example. So this is the metric for the de Sitter space, and this is the scale transformation. So xi is get scaled by some constant parameter lambda, and you should also change the time like this. You can just see from this metric that if t goes to t minus 1 over h log lambda, then this change from here will be cancelled by the lambda square that comes from this part. So if this is the scaling transformation that gives this metric invariant, then the scalar field will transform like this, and I should be able to understand that delta phi prime at x prime should be given by delta phi at x. So from there, I can see this should work out. Since we are interested in late times, so I can forget about the time dependence over here. So my delta phi, which is just a function of the positions in the late time slice, should change under this. The wave function is invariant, which we should demand. So that effectively becomes this psi for delta phi is equal to psi for delta phi prime, but delta phi prime is this one using this. Now, you remember in psi delta phi, in the exponential, we have this kind of object where each delta phi is associated with a O. To be more correct, if you are looking at the quadratic piece, it is multiplied by a OO. So for each delta phi, there is a O. And now this invariance of the wave function gets translates to this object being equal to this. Now here you can just do a dummy change of this x variable, and you can write it as before that delta phi prime is equal to delta phi of x by lambda, and then you can just do a dummy weight change where you call x by lambda as the x. So this x becomes lambda times x, and this x becomes lambda x, and these two sides should be equated. Now you see I have delta phi, so I can clearly obtain from here that Ox should transform to delta cube O delta times to O delta x. So this tells me how O should transform to keep the wave function invariant. And it was crucial that with each delta phi, there is an O in the exponential of the wave function. So this for infinitesimal scaling, where a lambda is 1 plus epsilon, with epsilon being much, much small. Sorry, this epsilon is not the Slogel parameter, any other parameter. So some small parameter less than 1. This OX, this translates to this. And this is exactly how an operator delta equal to 3 transforms in CFT. So that's how we see that, momentum space CFT, or, we have not yet gone to the momentum space, but the late time slice symmetries of de Sitter are same as CFT. So this we are making explicit use of that. So the word identities will be something like this, where I have a O 3-point function. So the delta of O given by this, it will hit each of these O's and it should be 0. So this is exactly the word identity of conformal field theory for some primary 3-point operators, 3-point function of primary operators in momentum space for the scaling transformation. And the CFT word identities in momentum space can be thought of as differential equations for these correlators. And then the question that we would ask is, can we solve them to get the we get the correlators? Now, to be very specific, I can write down the explicit form of these word identities. So for the exact de Sitter where there is no inflation, this happens to be the scaling transformations that keep this form of the metric intact, and for them we can obtain this to be the word identity written in momentum space. So this is just a Fourier transform of this or this for the scaling transformation in de Sitter. Similarly, for the spatial conformal transformation, this is the transformation. There is a vector b, which is a parameter of the spatial conformal transformation, like lambda was a parameter here for the scaling transformation. So this becomes the word identity for spatial conformal transformation, considering just 3-point function. I mean, you can understand, we can write it for 4-point function or any 6-point function or whatever. And these are differential operators which are given here, and this prime on this correlator means that I have stripped off this momentum conserving delta function, which should be there in momentum space because of homogeneity in the real space. Okay, and for inflation you should understand that there are small corrections, so you should just check how this delta phi transforms under this scaling transformation. But now you should be careful that I have a phi bar t also. Previously there was not, I mean, this was just a constant for pure de Sitter. But now I have a background which is just time dependent, and the change in delta phi should be demanded from considering this full scalar field phi, where I have a background plus this fluctuation. How does this whole thing changes under this scaling transformation? So from there you can see that you get an extra piece over here in addition to the piece that we had for the pure de Sitter case as well here, written in momentum space. And you can see that this is proportional to phi bar dot by h, which becomes 0 for the pure de Sitter case or exact de Sitter case. Now if you just demand the wave function is invariant, now there is a catch, because there is these two variations. Now you can see that the structure of this variation is inhomogeneous. That means variation of the delta phi doesn't have any delta phi here. So when I am looking for the wave function psi and I'm looking for the 3-point function word identity, I should also keep the 4-point function, because this delta tilde can act on one of these delta phi, and I will get rid of that delta phi because this is a inhomogeneous piece. So this delta will hit here and give me a delta phi back, because there is this delta phi. So this will still be a 3-point delta phi, but this delta tilde hitting on this delta phi will get rid of one delta phi in this 4 delta phi's. So this will be a 3-point function which can now potentially combine with this. So I'm not getting into the details, but if you follow the calculations, you will see that the scaling word identity for inflation becomes this object equal to something non-zero, which is proportional to this phi bar dot over h, which is basically this Slodel parameter or the square root of this Slodel parameter. So what I'm trying to claim is that this is the word identity of 3-point function, or in that sense any n-point function will be related to a n plus 1-point function with one of the momentum being soft. So this is some correspondence with the soft theorem that we know, where an n-point function gets related to an n plus 1-point function with one leg being soft. Similarly, you can also look for the spatial conformal transformation word identity, and you will see previously we had seen this equal to 0, but now we get something involving the 4-point function, again because of the same reason that I have explained here. But you know, this OOO word identity, this is an object in a CFT. Now, how do we get it in terms of delta phi, which is the real observable for inflation? Like, you know, in CMB, delta phi gets related to temperature fluctuation. So this is the 3-point function of the temperature fluctuations in CMB. So how would I get this from this? So for that, you should remember that the wave function is written like this, and this delta phi, delta phi, delta phi is this 3 delta phi's over here multiplied by a mod psi square. So from there, if you just take this psi, square it, and then keep doing weak contraction, then you will see that this delta phi will be related to this in this relation. It's some coefficient over here. So there are explicit expressions one can work out for this 3-point function, which this proportional to this slow roll parameters on the right hand side. So if they are put to 0, then you obtain this in the pure de Sitter case, or you know, pure or exact CFT 3-point functions. Otherwise, these are for inflations. And similarly, one can also obtain the 4-point correlator and check that this word identities are indeed matched. Okay. Now, I mean, let me come back to this question, that how do we compute this 3-point or 4-point functions in inflation? Okay, I told you that once I know this wave function, I can put them as insertions in a further integral, and I can compute this endpoint function. And you should remember, this is psi has these objects on the right hand side. All of them, I'm not writing others. But then what we should do is exactly big contractions, as I just told you, and these are like Feynman-Witten diagrams. So let me give an example. If we are looking for a 4-point function of delta phi, this is in the cosmological language will be termed as the trispectrum. So 4-point function of temperature fluctuations. So then what you have to do is this, look at this, where I have this four of these delta phi's, which actually come from this. I have 4, and from mod psi square I look at this term. These are like vertices, these are in the exponential. I bring down 2 of them, 1 and 2, and then we contract this delta phi with this delta phi, this delta phi with this delta phi, this with this with this, and this with this. So this becomes some picture like this, where there are 4 delta phi's. These are the external legs, which are like these green contractions here, and this is the exchange delta phi, which is this. These are called the Feynman-Witten diagrams. So this happens to be the bulk to boundary operators, bulk to boundary propagators in de Sitter phase, and this is the bulk to bulk propagator for a scalar in the bulk of the de Sitter. And if you know these propagators and this vertex over here, then you can compute it. There is another possibility where you bring down 2 of this object, and as you can see, after this weak contraction, that will give you a bulk graviton exchange diagram, where there will be 4 bulk to boundary scalar propagators, and there will be a graviton exchanged, meaning this gamma, the tensor perturbations. And then there is also a possibility that I bring down one of this 4-point vertex, and that will give me a bulk contact diagram. But one can check that all of them will contribute, but in the leading slow roll approximation, this wins. These and these are all suppressed in the slow roll parameters. I'm not getting into the details. I can tell you if you want, but if you then focus on just this diagram and compute this Feynman diagrams, then you will get what you need to compute delta phi delta phi delta y in the leading slow roll approximation. Now for the 3-point function, you should look at this uh, this word identity that we derived before, but this gets related to the 3-point function of delta phi, and this gets related to the 4-point function. Now we know here we have computed the 4-point function, which is given by this bulk graviton exchange. And then this word identity tells that put one of the leg in with the soft momenta, and then you will get the 3-point function. So from the Witten diagram point of view, the 3-point function happens to be like this. The understanding of that happens to be that take the 4-point function, and in the one of this external leg, replace it by the fiber dot, which is the background time derivative of the background value, which happens to be sitting here. So you take a 4-point function, which in the momentum configuration will look like this. So these are all momentums, and let's take this is k1, k2, k3, and k4, and then you take this to be very small, so it effectively becomes a 3-point function. But this this extra factor gets attached to it. So intuitively speaking, I mean, this can be made more rigorous, but you can obtain using the word identity the 3-point function, which has an interpretation of this kind from the bulk Witten diagram point of view. Now this ends the wave function way of computing scalar correlation functions, and then I will maybe I will have 10 to 15 more minutes that I can talk about the alpha vacua. Okay, any questions so far?
So there are some diagrams in the 4-point function which are already suppressed by the slow roll parameters, but you're using this word identity to find the 3-point function, and the coefficient of the 4-point function already has another slow roll. So it will be like, is it?
No. So the 4-point function in the leading slow roll approximation does not vanish.
Okay.
What this word identity tells you, which I didn't get to, is that the 3-point function in the leading slow roll approximation, so if the 4-point function gets the leading contribution from this diagram, and which is non-zero, you can evaluate this diagram, and I can tell you the paper where this is done, then the 3-point function leading contribution will also come from that if this word identity has to be true.
Okay.
Now you calculate 3-point function independently from the informalism, and you will see that that's indeed true. So the statement is that the delta phi is further suppressed by a slow roll parameter. So that's why the 3-point function for the scalar 3-point function, so the scalar bispectrum is so hard to observe. This is not true, for example, for delta phi Tij, let's say, or sorry, gamma ij. That's not suppressed compared to, I mean, that's you know, the value is much more than this. So when there will be an observation of the non-Gaussianity, people should look for delta phi gamma ij and not delta phi delta phi. That's what we learned from this analysis.
The three possibilities that for the 4-point function, you said one of them is leading, but leading in the slow roll approximation.
Yeah, I'm only talking about slow roll. So
Okay.
this diagram will also be here and make some contribution, but that will be even suppressed.
So even suppressed. Okay.
So there is no hope of seeing it in near future.
Yeah.
Okay.
Okay.
Any other questions?
Yeah, so one small question. If
Yeah.
when we do this kind of filtering in de Sitter type of thing, is there any subtlety associated with the weak rotation, or is it
Okay.
okay because we are doing in Bunch Davis or something?
Yeah, so we are doing it in Bunch Davis, but so when I did this bulk graviton exchange over here, this diagram, when I computed it, I didn't touch that at all. So what we do is like we do a double weak rotation and go from de Sitter to Euclidean ADS. So
Okay.
then we use the techniques of ADS CFT, and
Hmm.
there these diagrams can be obtained. But one can in principle do this calculation. So compute the result in the ADS CFT,
Hmm.
and then take double weak rotation back and get the de Sitter answer.
I see. And that
So
is okay. That is something we can do.
that's what we can do. Actually, the check is what I will probably talk about now. That this in-informalism is the age-old way of computing correlation functions. So Sloth, Seri, Vernizzi, they all computed this 4-point function using this in-informalism long back,
Hmm.
and we computed this using this, and they exactly matched.
I see. Okay. Okay.
But the subtlety is that, or not the subtlety, the interesting thing is that in the in-informalism, as you know very well, the 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 answer is not written in a way such that this conformal symmetry is explicit,
Right.
which is much more explicit in this wave function way of doing because of these coefficient functions be getting associated to it.
Mm-hmm.
But you exactly get the same result that you can compute with in informalism.
I see. I see. Okay.
So that's also an explicit check, and also in principle, yeah, this DS calculations one can do map to ADS, and then this Bunch Davis condition is exactly the regular ingoing condition you set at the horizon of ADS
Okay. Okay. I see.
in the Eddington-Finkelstein coordinates or whatever. So then you can do then it's a well-posed boundary condition problem. So in the de Sitter also, uh, just has to be nice. So I have 15 more minutes, Nirmala.
You can take your time, Nilay. I mean,
Okay,
just
okay,
take
sir.
as long as you need.
No, 15 minutes I'll be done.
Okay.
Okay, so I didn't talk about this in-informalism way of doing the bulk calculation because, honestly speaking, I never worked it in any paper, but uh, this is the as I was saying, traditional way of computing correlation functions. So just let me mention some highlighting features of that. So in particle physics, when we compute scattering amplitudes, uh, we basically start with an in state, which happens to be the eigenstate of free Hamiltonians at far past, and we evolve it, and then there are some interactions which are given by some operator insertions, let's say, and then we flow out to the far future where we again have free theory approximations, and we can figure out the eigenstates of the free Hamiltonian. So this is in a sense an in-out correlation function, the S matrix that we compute. But in cosmology, we just have one time slice where we do everything. And in the far past, we may start with an in state, then we can flow in a contour in the time, this is the time direction. We come to that time slice where we would like to compute the correlation function, which may be the late time slice of the de Sitter, and then we follow the contour back and go to the the, the dual in state or the bra in state. So that's why this is a in-informalism as compared to the in-out uh, formalism of S matrix, and this is also called the basically the Swinger-Keldysh formalism. So in this in state, if you have, let's say, product of three scalar perturbations, or which are inserted at this t. So these are the boundary values at the late time slice of the eta equals to 0 slice of inflation ends, and then there are insertions. So that happens to be this slice, and this qt is the product of this, and I'm writing it in terms of the momentum modes. So then this path integral is basically, in the path integral formalism, this is basically written like this, where I start from the vacuum here, then I use this evolution operator, where I've written the interacting Hamiltonian in the interaction picture. This product also I've written in the interaction picture. So I start from this. So this operation represents this motion. Then I appear here, and then I insert these operators here. And with this, I flow back to this. So that can be obvious from the sign of this evolution operator. And this t and t bar are just making sure that in this path integral, when I'm inserting in between states over here, they're all time ordered for this path, and anti-time ordered because I'm going against the time for this evolution. So that's why this t bar and t. But yeah, I mean, if I'm working in an interacting in a perturbation theory, then I can start from here and obtain an equation where this is just the commutator of the insertion operators with the interacting Hamiltonian, both in the interaction picture. So this is just the brief sketch of the formalism, and with this one can come back and compute all these correlators over here. And as I told you, the way you calculate this, the slow roll de Sitter case, slow roll inflation case, this Feynman-Witten diagram calculation over here exactly reproduces the result that one obtains using this formalism, where you insert 4 delta phi's here, and that's what we checked in one of our papers. So now let me talk about this alpha vacua very briefly. So this alpha vacua in de Sitter space, the main question that we are trying to understand is, what was the initial condition for inflation? So did inflation start with the Bunch-Davies vacuum, or did it start with in alpha vacuum? And since both of them are conformally invariant, so we can use the CFT techniques over there. Now, let me define what are alpha vacua. So, let me focus for this part of the discussion to exact de Sitter, or ignoring the slow roll parameters for now. So, this is my de Sitter metric written in conformal time coordinates, and I'm considering a free massless scalar field theory coupled to this minimally coupled to this de Sitter 4 metric. So basically, I'm doing QFT in curved spacetime. I can mode expansion this phi, where this V and V star are obtained as the classical solutions of the Klein-Gordon equations that follow from this equation, and this happens to be this, which comes from some Bessel functions. But one can check that these are the classical solutions, and this A and A dagger are the creation and annihilation operators, and they follow the standard commutation relations. Now, the Bunch-Davies boundary condition tells us that this AK kills the vacuum. This A annihilation operator kills the vacuum. Now, why is it special? Because while writing this as a solution of the classical Klein-Gordon equation, I've assumed that the equivalence of the Bunch-Davies boundary condition that I discussed before. So this is the Bunch-Davies boundary condition, let's say, due to this mode expansion, as I've written here. But since we are doing field theory in curved spacetime, and there is a time-dependent background, So there is no global definition of time, and hence we can do probably a different mode expansion. So this is exactly the story of the Rindler vacua that is responsible for Unruh effect. So I can do a mode expansion in a different basis, and that basis U and UK star can be linear combinations of the solutions that I obtained here. So I obtained V and V star, that I can do some linear combinations by some parameters A and B, and I can do the mode expansion in that basis, and hence I will obtain two different creation and annihilation operators. And this A and B has to satisfy some condition, and there you can see that this is just to make sure that this phi, this U has unit norm. So for which you can see that there is a possible parameterization of this parameter A and B in terms of this alpha and beta written here, such that this condition holds, and that's how this linear combination A and B is also can be thought of in terms of alpha and beta, and that's why this name alpha vacua. So the statement is that if you take alpha going to zero limit, then this becomes 1, so this remains, this drops out because sine hyperbolic 0 is 0. So you get back this Bunch-Davies vacuum. So the Bunch-Davies vacuum is is one of the member of the one parameter family of solutions that I'm talking here, which is parameterized by this parameter alpha and beta. So now, since we have a new annihilation operator, I can define a new vacuum which will be annihilated by these B modes or these B operators, and one can check that this new vacuum is basically a Bogoliubov transformation or a squeezed state in terms of, sorry, I should write it. This 0 is the standard Bunch-Davies vacuum. So the alpha vacuum happens to be some squeezed state of this Bunch-Davies vacuum, and that's why I mentioned before that this alpha vacuum physically means that maybe when inflation started, there were some particles leaving, something else was there, and hence it was not a vacuum but an excited state. But exactly this excited state, because we still want to use the fact that conformal invariance was indeed a symmetry that was guiding this thing. Now we can also do something more. We can think about interacting field theories in de Sitter. Let's say I put a cubic interaction, and then I can exactly do the 3-point function using the in-informalism. So here comes that subtlety which someone was asking me, that what will be the difference in the wave function way of doing the Bunch-Davies condition and the alpha vacuum. So no one has done it, but people have used in-informalism. I mean, we have used in-informalism to compute the 3-point function of some scalar field in de Sitter, in exact de Sitter, using the in-informalism. So this is straightforward to obtain. Once we know the interacting Hamiltonian, I can go to the interaction picture and I can insert the operator phi 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 in the interaction picture, and I can just do the calculation. And I'm not writing the exact result, but the final answer turns out to be the cos hyperbolic times alpha times the Bunch-Davies answer that you would have obtained if you had done this same calculation in the Bunch-Davies vacua, times sine hyperbolic alpha times a new term over here. So this is the new contribution from the alpha vacuum answer. So this whole thing together is the alpha vacua answer, but it also guarantees that if you take alpha going to 0, this term drops out and you get back the Bunch-Davies answer. So this is a bulk calculation, but a bulk in calculation. Now the question is, what is the CFT interpretation? I mean, do we have any CFT interpretation of this? So we have obtained a bulk result like this, which we can relate to some OOO in a 3D CFT. But in 3D CFT, at least in position space, we know there is a unique answer. then where does this extra piece goes in? If because the expectation that there should be something in terms of CFT is because we are using a conformally invariant vacuum, so we are not disrupting the conformal invariance, just changing from bound states to alpha, but we are getting some new answer. And how do we incorporate that in the CFT way of understanding? So that's what we attempted in this latest paper with Sachin Jain in Isaac Pune and three grad students, Shumon Kundu and Sunil Sake at TIFR and Abhishek Mehta at Isaac Pune. So we wanted to see that this 3-point scalar correlator in the momentum space, when written in momentum space for the alpha vacua, should have this structure also. Sorry, should have this structure also, where it should be cos alpha, and you should expect that this probably should match the Bunch-Davies answer. And that's indeed true. So when we are doing momentum space word identities, so we don't really have any formulation of uh, we don't have any formulation which is like we formulate quantum field theory in position space, where we know that there are conformal transformations which are angle preserving transformations. Then there is a field theory which falls in some representation of that symmetry group, and then we can argue that the 3-point function is exactly fixed and all. We don't have that formalism in momentum space. So understanding conformal field theory in momentum space is by itself an interesting independent question, and people like Skenderis and collaborators have done huge work on that, and in still today's time people are also working on that. But we want to use that formalism where one would study conformal field theory in momentum space and say something about cosmology. That was the idea. And then in the alpha vacua context, then the only platform that we have in momentum space are word identities. So we somehow start with the word identities. We write down the differential equations for the word identities involving 3-point function or 4-point function or n-point function, and we look at them as differential equations and try to solve them. So that's the basic idea. So in those solutions, we should look for these extra alpha vacua answers, and that's what we did in this paper. So let me just now tell you the final answer. So now I am doing conformal field theory in momentum space. We can forget about the inflation connection for now. So these are the special conformal transformation word identities where I'm looking for some d-dimensional Euclidean CFT, and for the inflation context I should put d equal to 3. Delta I is the dimension of this operator O, this P, K, J, where this K is the Lorentz index, like the component of the momentum, and J runs from 1 to 3 because this is a vector. Sorry, this has P1, P2, P3. There are 3 insertions. So if I was looking for 4-point functions, this J would run from 1 to 4. J is that number index. K is a vector index. As we know, special conformal transformation is generated with a parameter vector B. So I should have a vector equation, which is not true for the scaling word identity, which is just this. So these are just my starting point, and I've probably discussed this before, that if we have a scalar in the CFT with a dimension delta, say then for delta equal to 2 corresponds to, in the de-Sitter side, de-Sitter 4 side, this corresponds to some conformally coupled scalar with mass given by this, and delta equals to 3, as we have seen before, corresponds to massless scalar field in the de-Sitter 4. Similarly, for if I have a spin 1 conserved current operator in the CFT, that would correspond to massless vector field in the bulk, and similarly the graviton or the tensor perturbation in the bulk corresponds to delta equal to 3 spin 2 conserved current, or which is probably this, which is the stress tensor. Now I kind of ignore the details. So this is the solution of the word identities. This is the word identity. So 3-point function, solution of that differential equation. One can write it at least, you know, in principle, in a very formal language like this, where you should see that there are these functions, product of them, three of them. So this is called the triple k integrals. So each of these k are the Bessel k functions, and and this is some integration over the z. So if you have the de Sitter thing in mind, you can see that this is like the three Bessel functions are exactly the bulk to boundary propagators, and z is that bulk point which should be integrated over the full of the de Sitter space. But yeah, I mean that we don't need to mention. This is just a mathematical statement that this is the solution of the word identities, scaling and special conformal transformation, which I wrote before. Now if I put d equal to 3 and delta equal to 3, then I will get what I know, uh, this operator, which is of interest to delta phi, delta phi, delta phi propagator in the in the in the inflation or de Sitter context. So for that, you can check that this is like the final expression where you have some coefficient, something which is basically some structure given here. I'm sorry, I'm kind of going fast over it because this is just some mathematical details. The important thing is that there are 8 possible terms on the right hand side, because this m n1 n2 n3 is some coefficient, but n1 n2 n3 each of them can be plus minus 1. So there is a 2 to d3, 8 terms on the right hand side. So there are 8 parameters on the right hand side, but if you organize it properly, you will see that amongst these 8 of them, they always appear in these 4 combinations. So basically, there are this 4 structures on the right hand side, and then so there are 4. What I should say, final result is that this O 3-point function for delta equal to 3 and in d equal to 3, there are 4 independent solutions on the right hand side. So you already see that if all these 4 has to be there, then we are in business, because one of them should be the Bunch Davies and the other 3 should correspond to the alpha, but not 3. We should get 2. And that's why we should remember one more thing that we need to impose, which is the permutation symmetry between K1, K2, K3. This O are all identical operators. So if I change the pairwise momentas, K1, K2, or K2, K3, or K1, K3, or 2 cyclic perturbations, then I can get rid of 2 of these coefficients on the right hand side. So finally, I have 2 uh, coefficients times some structure on the right hand side, and the structures are exactly written here. You can see. Now if you compare this with the so what I'm obtained is that the CFT calculation, solution of word identity plus exchange symmetry, gives me this result, and the bulk result, which is the delta phi, delta phi, delta phi of de Sitter 4 result, that gives me this expression. This is some very complicated result, but on the right hand side there are only one parameter. But I can compare this. I know the structures over here, and I also know each of these structures. So if I compare, then I can see that this one relation between the coefficients in the CFT answer gets related to the bulk parameter. And so this is now we are in business that we have accommodated so this part is actually the alpha vacuum answer, and this corresponds to the Bunch Davies answer. But we have not yet understood one that I would like to mention, which is that but in position space we know that there is only one answer. So if we would like to take that answer and to Fourier transform, then why am I getting this alpha vacua answer? I mean, it should correspond to Bunch-Davies, and it actually really has to contribute, because if you should understand. I mean, I'm kind of going fast over here because these are all just calculations, but uh, what you should remember is that there are certain terms in this OOO which are inconsistent with OPE expansion. Okay, so the final result tells is that when I'm doing it from the momentum space word identity solution, then I have to take care of the OPE consistency separately. If I don't impose the OPE consistency, then I get these extra alpha vacua answers. But when I do it in the position space and the way I build it, then it's uniquely fixed to be the Bunch-Davies answer. So I take into account the OPE consistency in position space very, very trivially. Now, now here you can tell me, you can see that this, let me get rid of all this. So there is this folded limit singularity. So how to understand this OP limit in the momentum space? So let's say I have this correlator OOO in momentum space, which should be some Fourier transform of the position space answer. This is just a Fourier transformation, and then I in this Fourier transformation, if I if I impose OP that this O and O comes together, then I should impose something like this, that O and O, where x goes to 0, can be given by this. And now, if you substitute this in this Fourier transform over here, you get a 2-point function, and the dimension fixes this 1 over x cube, because this O is dimension 3 operator. So that's why this 1 over x cube is here. So that's also, that should also come here in this thing. And then if you, so you see this 1 over x cube, I probably have missed this x cube here. Anyway, so this thing is here. Now we know this 2-point function in position space. 2-point function is this. And if you know, if you just impose everything, so in the momentum space, it turns out that this OOO K1, K2, K3 should be exposed to this limit, where two of the momenta are of the same order, the magnitude, which is much, much larger than the third momenta. So if I have to check OPE consistency in momentum space, this should be imposed to this 3-point function, and the answer should come out to be this, which I get from this analysis over here, which is I have derived here. But now, if you take the answer that you obtain from solving the word identity and then imposing the exchange symmetry, the permutation symmetry, then you get these 3 terms, for which you will see that if you take this particular limit, so there are this log, okay, consider this as k1 plus k minus k2 minus k3. So if p2 and p3 are of the same order, and they are very, very large than this, so you see in this limit, you will see there is this terms which diverges, or it's not consistent with the OPE limit. So that's what we checked. So the statement is that, final summary is that as solutions to momentum space word identity, the Bunch-Davies answer corresponds to Euclidean CFT correlation functions. The alpha vacua answer corresponds to Euclidean CFT correlation functions, but not consistent with OPE. From the de Sitter perspective, what are the pathologies associated with this alpha vacua? So I did the alpha vacua, I hinted, or I just mentioned the alpha vacua answer of calculation of ininformalism, calculation of alpha vacua. So if you compute the stress tensor 1-point function in that alpha vacua, that also diverges, which signals that the back reaction from the scalar field is too high. and probably this probe approximation of taking a scalar field in an exact de Sitter is not valid, but probably one can use appropriate renormalizations or appropriate counter terms to take care of this divergence. So that will make this alpha vacua result not so pathological from the de Sitter perspective, but in the CFT perspective, it looks much more dull because to accommodate this alpha vacua, we should have some CFT without the OPE consistency, operator product expansion consistency. But we don't. I don't know any CFT of that form. But maybe there are some CFTs where, I mean, whether we call it CFT or what, I don't know. So this is still an open thing to kind of make sense of this. But there are studies where people say that at least from the de Sitter perspective, people talk about this alpha vacua and their observational signatures. So, well, what is the observational signature? So you see that the 3-point function turns out these things. So now if you observe the 3-point scalar correlator and see this thing which is extra compared to the Bunch Davis result, that's how you can differentiate between whether inflation started in Bunch Davis or in alpha vacua. And people say that probably one should properly take care of this renormalization of these divergences, and maybe alpha vacua states are not so bad. But then from the CFT perspective, what to do with some kind of CFT but not consistent with OPE is still I don't know any answer of it. So yeah, that's where I would like to stop. But yeah, sorry for going over time, and yeah, thanks for the attention.
Okay, thanks a lot, Nilay. So that was really an excellent talk, and I think really you should turn this into some kind of mini course.
I don't know. I was just also, I mean, okay, I was very ambitious. Before the last presentation, I just started writing things and it came out to be this, and I was hoping maybe I would complete it in one. But now I realize if I really need to do something, if someone wants to learn this in informalism calculation, that would take one more lecture to learn this, CFT. So yeah, we did a lot of thing over here also. We just didn't look at OOO, but we can look at any spin operators by using something called this spin raising or lowering operators that Joe Pinedones and they have constructed. So they basically take you from it allows you to move in the solution of the word identity sector, but changes the dimension or the spin of the operator. So they are still solutions of the word identity, but you can change the spin of each of them or all of them together. So knowing this OOO answer, you can get all spin correlation functions in momentum space CFT. But that was known in Bunch Davis. We checked that that you can do in alpha vacua as well. So this kind of answer with a seed here you can do. So yeah, but that would take a lot of time for me to come.
Okay, so we can start taking questions now. So if anyone has a question. So one thing one can notice here is that so OP limit not existing is like some kind of, it's a problem at large momenta or at short distance. So some kind
Yes.
of issue seems to be at short distance
Yes, yes,
physics.
yes. That's why in this sense, this is related to some
Some
divergences.
divergence, some renormalization,
But
ambiguity.
there are works, Kevin Goldstein and people.
Mhm.
Actually, and the Strominger worked on this alpha vacua. What is the understanding of that from the DSCFT perspective?
I
They
see.
say it's marginal deformation of CFT,
Uh-huh.
but they don't really get into these issues of. But then Kevin Goldstein and all, from the bulk perspective,
Mhm.
they have looked at the alpha vacua and they said that there are indeed counter terms. So the statement is, from the bulk perspective, people say that alpha vacuums are not so bad.
Mhm.
But then from the safety point of view, it shows something. So I don't know how to make any.
It seems like a very interesting problem. Like,
Yes,
and
yes,
that how
yes,
do you match these two things?
yes, yes. But calculationally, they two match exactly. Like
Mm-hmm.
if you compute it, this I mean I didn't write this down explicitly, but oh well, I was saying somewhere they just match exactly with the bulk calculation. The solutions of the word identity and the bulk calculations, they just exactly match with each other.
So
Like,
maybe there is still
yeah.
some problem in bulk which has not been discovered. Or
No,
maybe
but this renormalization issue is also, I think it's not well settled.
right, right,
I mean, whether you can properly renormalize it. So
right.
some people say that yeah, it's not that bad,
Mm-hmm.
but it's really okay. This is indeed an interesting thing to.
Any other questions? Okay, if there are no more questions. Let us all thank Nilay once again.
Okay. Okay.
Okay, so now let me stop recording and.